Good afternoon. I'm going to be presenting my operational amplifier assignment to you. So I'm going to go over how operational amplifiers work, different types of operational amplifiers, some of the key terminology when we talk about amplifiers, and different ways that we can use them. So the first thing I want to go over is some of the key features of operational amplifiers. So the first feature I want to talk about is the variability of operational amplifiers. And so operational amplifiers can be used in a ton of different ways and different configurations. As you'll see later, we can connect different things to the input and output terminals. So we can apply feedback from the output terminal to the input terminal. We can connect a voltage divider to the input terminal, and we can use single input, we can use double input. Basically, we can use a number of different configurations, and it completely changes the outputs we get and the effect of the amplifier. And so that's one of the huge benefits of the amplifiers, is the functionality of them is so varied, which also makes them really powerful. So the next thing I want to talk about is saturation. So this is a key feature of the operational amplifiers because it basically helps us to amplify things. So as you'll see later in the difference amplifier, we can basically take a small difference between the input and output terminals, and we can saturate that difference so that we get the full output that we are expecting. So if typically we're expecting a 5-volt output and our supply is 5 volt, even if we only have a difference of, say, 0.1 volts, we can amplify that to 5 volts. And so that's the saturation happening there. The next feature I want to talk about is feedback. So feedback is used to control the amplification or the gain of the device in a predictable way. So as you'll see later on, when we use feedback, there's a couple of different types of feedback, but we can use it to basically regulate the amplification of the circuit and control basically how much it is amplified by varying the resistance applied on the feedback. So from the output back to the input terminal, we can change that, and we can control the whole functionality of the circuit using that. So when I was doing the reading, there were a number of rules that they mentioned, and so I thought those would be important to bring up in the presentation. They're just good ways to think about operational amplifiers. So the first rule is for an ideal operational amplifier, which obviously doesn't exist in the real world, but it kind of shows what would happen. For an ideal op amp, the voltage gain is infinite. So the amount of gain that we can have is absolutely infinite. You can take any input and amplify it to an infinite amount. For real operational amplifiers, that's not practical. So typically it's from 10,000 to a million would be our gain. So 10 to the 4, 10 to the 6. Yeah, so that's more realistic for actual amplifiers. Rule number 2 is for an ideal operational amplifier, the input impedance is infinite and the output impedance is 0. And so essentially this means that the resistance on the output should be 0. So basically there's no voltage drop or anything across the output. We just have full output. Again, not practical. And there's no drop on the inputs as well, which again isn't actually how it goes. Rule number 3, very similar. The input terminals of an ideal op amp draw no current. So essentially this is saying that there is no natural draw of current, but we know that there can be a slight difference between the potential on one side to the other, and so that naturally will cause a draw of current. And so this can happen between terminals, and it's just something in practical operational amplifiers that needs to be remembered. And rule number 4 any voltage difference between inverting and non-inverting inputs will be fed back through the op amp to keep it equal to 0. And so essentially what this is saying is that when we use feedbacks, there is a balancing act that occurs. So when we first apply voltage through the operational amplifier, there would be no feedback currently. So as soon as it goes through, there is now feedback, and so that goes back into the one input, and now it does it again with the input plus the feedback, and so that goes through the amplifier and the feedback changes. And so that's a consistent cycle until it comes to a balancing point, and that's it trying to equalize itself and reach 0 essentially. The next thing I think is important to talk about is inversion with operational amplifiers. So obviously these are definitely two of the most important features, or one of the most important features, and there's two different types of inversion that we can see. So there's the inverting amplifier, which we have negative feedback. So as I just mentioned, feedback, we have negative feedback coming from our output side back into the negative terminal, or the inverting terminal. And so this causes a different calculation in gain because our feedback is on the output, and we are subtracting that from whatever's coming in the input. So basically our V out is going to be gain times V positive minus feedback times V out. So that's the equation when we've got an inverting amplifier and we've got negative feedback happening in it. And the gain there is going to be negative R2 divided by R1. So R2 is going to be our feedback resistor. And we've got a voltage divider, and so that's why we see this equation happening here. So it's going to be basically the ratio between this and R1 coming in. And it's going to be negative because even if we applied positive voltage over here, it's going to go through that negative terminal and it will be inverted because that's the inverting terminal. And so when it comes out on the output side, it will be negative. So that's why we've got a negative ratio happening here. And as we can see from the waveforms shown, we've got our input up here, which is just typical sine wave. And you can see where this one goes up, this one will go down, and vice versa. And so you can see why it's called an inverting amplifier. And it also shows how it's amplified because these amplitudes are much greater than in the original. And so, basically the same, but the opposite is the non-inverting amplifiers. And so these take positive feedback. So feedback from output going through the resistor to the positive side. And so in this case, we got the voltage divider and we calculate our gain based on, or our output based on the gain of the amplifier times feedback times the output minus the voltage. And so, yeah, this is very similar, but our gain is calculated a little bit differently in this scenario. And so the reason we are multiplying feedback by V out, it's because that's what is coming in here, right? You have your output times your feedback, and then we're subtracting that from our voltage in. Yeah, so it'll decrease it just a little bit, but it's all based on that gain, right? And when we multiply feedback by V out, that's going to get bigger. So, yeah. And to calculate gain for this, it's going to be 1 plus R2 divided by R1. And so if we were to rearrange this, essentially we would have R1 plus R2 divided by R1. And so again, you've got that voltage divider equation. But when we start moving things around, we can see that basically it starts at 1 above it, and then it's all dependent on the ratio between these two. And so as the name suggests, when we look at the waveform here, it's not inverting. So when this goes up, this one also goes up and it follows that line, but it amplifies it. And obviously that is the key function of this one. So next I'll look at some types of operational amplifiers that I wanted to mention. So I think two of the biggest types are summing and difference amplifiers. And then I also thought the integrator amplifier was very interesting. So the summing amplifier, basically it's going to sum the two voltage inputs. And so when we look at this circuit diagram here, we can see that there's a voltage divider happening up here, as well as the typical voltage divider that we see between feedback and input. And so this uses, the voltage divider on the feedback, and it amplifies the addition of the two inputs. So when we look at the equation, it makes a little bit more sense. So we've got R3 divided by R1, and so R3 is going to be our feedback, and R1 is our voltage 1 source. And so we've got a voltage divider here. So voltage comes in, divided, and then comes down. So that's where we get the first component of this. And then we look at the second component. So we've got the feedback loop. So R3 again, voltage divided with R2. And then that's multiplied by our voltage source on R2, V2. And so we add those two, and that's what's going into the inverting terminal there. And so that's what makes it negative. And when that comes out, that's our output. So it kind of tracks and why this equation makes sense when we look at this diagram there. So the difference works a little bit differently. The key thing with this, and as you see in this configuration, the resistors are balanced. So you see R2 here, or sorry, R1 here is at 10,000, and R1 here is at 10,000. R2 and R2, both 100,000. And so that balance ensures that the two inputs are also balanced. So if we weren't to have those balanced, it would be a much different equation and a little bit messier in the difference between the two. So it would be a little more biased towards one versus the other. So basically, this takes the subtraction between the two voltage inputs. And because we've got those resistors balanced, we just have R2 divided by R1 multiplied by that difference. So that's basically gain times the difference. And that's what gives us the output in this one. So, this one adds the two, this one subtracts the two, but we can see how those can both be very useful circuits to have. And then I thought the integrator op amp was very interesting. So this one uses a capacitor, unlike all the other ones. And so we know capacitors charge and discharge. And so when this is connected to our feedback, our inverting terminal here is going to be charging and discharging and receiving more feedback sometimes than other times, which I think is very interesting. And so that's what gives us this interesting sawtooth output. The output here is equal to the negative integral of the input voltage. And so that's why it's called the integrator circuit, it's essentially simulating an integration of this input over time. And so the way we calculate the output here is 1 divided by our resistance times our capacitance times the voltage in over time. And that's how we can calculate this. And I think it's a very interesting configuration of this circuit, and kind of cool to see how the capacitor can affect it very differently, because all of these outputs would be a square waveform. So this gives us a little bit more of an analog signal there. So I now want to talk about some real life amplifiers that we see. One of the most common, I think, is the audio amplifier. And so this is what we see pretty much everywhere, microphones, speakers, all sorts of things. So these are designed to operate within audio frequency spectrum, which is 20 to 20,000 hertz, which makes sense. These are specifically for audio applications. And so they work from a very high frequency spectrum to a very low. Um, so one of the big features of this is low audio band noise and crossover distortion. So, it's essential that it not distort the signals when it amplifies them, because you don't want your audio to, be pitched in a weird way or have some sort of distortion when it comes through. You basically just want to take that signal, amplify it so it's louder or quieter, but leave the integrity of the signal alone. So that's what these are key for as well. And as I mentioned before, these are common AM/FM receivers, intercoms, auto circuits, basically anything where you're trying to take some sort of audio and send it through. The next real life operational amplifier that I want to talk about is programmable amplifiers. So these can be used in very low voltage applications, which is a huge benefit of them. And basically by controlling the current supplied to the programming pin, we can allow for tons of different changes to the circuit. So we can alter the power dissipation, the input offset, the slew rate gain, gain bandwidth. We can do a number of different things by just applying current to this single programming pin, which allows us to completely change the performance of the operational amplifier. And I'll mention what those terms mean in a minute. Things like slew rate, I'll kind of go over what that is. But first I want to talk about single supply amplifiers. So this is another very useful amplifier circuit. This one, basically, as the name suggests, it only takes one input, and then the other input is typically tied to ground. So that's our reference voltage is 0 volts there. And so these can be great because you only need one input to do the amplification. The only downside of it is because it's tied to ground, there is no input below 0. There's no output below 0. So you can only show positive outputs, which can be not great for AC coupled applications because half of your signal basically disappears because of that. So some of the definitions here, common mode rejection ratio. All these definitions came up in the reading, and so I thought they'd be important to mention. They are key terminology when we talk about operational amplifiers. So common mode rejection ratio, this is the ratio between different signal and common mode signal gain. The greater the CMRR, the better the performance of the operational amplifier. And so it basically just defines the difference between the two, and how much gain we have between the two. And so, the greater, the better for our operational amplifier. Differential input voltage range. So this is the range of voltages that may be applied between the input terminals. And so basically this just defines the maximum difference we can have in voltages applied to the terminals and still have predictable outputs and have the op amp work as expected. Differential input impedance. So this is impedance measured between the non-inverting and inverting terminals. So this is just natural resistance that happens between those two. Input offset voltage. So this is the amount of voltage needed to be applied to one input to zero the output. So essentially, sometimes there is as with real operational amplifiers, things aren't ideal. And so we may need to apply a voltage to one side because there could be a bias towards the other side. And so by applying a small voltage to the one side, we basically zero the two, so they're at an even level. So, we don't get saturation accidentally by one of them being higher than the other, because we know operational amplifiers will saturate any imbalance between the two inputs. So it's important to make sure that they are equal and zeroed. Next, we've got input bias current. So this is the average of the two input currents, shows bias towards one versus the other. So this is very similar where there can be a bias between the two inputs, and so it could draw more towards one versus the other. So continuing this, input offset current. So this is current that needs to be applied to the terminals to offset that variation. And, similar to the voltage that I just mentioned, sometimes we just need to apply a little bit to ensure that things are going to be balanced and it's going to work as we expect it to and not randomly saturate things. Voltage gain. Obviously, that's typically what we're doing with operational amplifiers is we're boosting the voltage on the output side. So a typical op amp has a voltage gain of 10 to the 4 to 10 to the 6, mentioned that before, which is 80 to 120 decibels. So obviously we talk about audio a lot, so decibels is an important thing to note as well. And 1 decibel is equal to 20 times log 10 of the gain. Next, we can look at the output voltage swing. So this is the peak output voltage swing referenced to 0 that can be obtained without clipping. So basically the whole range of outputs that we can have before we start clipping it off. And so at a certain point, the outputs might be so high that it starts getting clipped, or the difference between the two input terminals might be amplified to a level where it gets clipped off. And essentially just can't go above that. Next, we've got the slew rate, and so this represents the maximum rate of change of an op amp's output voltage with time. So this is essentially the rise time and fall time of a signal. So the higher the slew rate, the faster it's going between that rise and fall time. And finally, we've got supply current, and so this is the current required to power from the power supply to operate the op amp with no load and an output voltage of 0. So this is just base requirement for the op amp to operate. So what it needs to be supplied with so that we can use the operational amplifier as expected. So again, powering the op amp. Most op amps require both positive and negative input supply to allow it to output both positively and negatively. As I mentioned, single supplies only use one polarity, so they can't output that negative signal, which obviously, again, as I mentioned before, not good for AC applications. And by applying a DC offset on the input, we can limit the input signal to allow it to only operate between 0 volt and that offset. And so when I was talking about clipping before, this is where we would see that clipping occur, is, it's only going to go up to that DC offset, and then there's nothing above it. So it's just maxed out, it's fully saturated. And another benefit of this is another feature of this is when we apply it to one of the terminals, that offset brings it up so that essentially it will never go below 0 because it's always offset to 0 or greater. Yeah. So now we can look at comparators. Comparators are super useful operational amplifiers and have very interesting functions. So comparators take 2 input signals, or basically one signal and one reference signal. The outputs are saturated so that they reach that full offset even when the difference is very small. So that's obviously a typical function of an op amp. Comparators are not frequency compensated, and so they can't be used as linear amplifiers. So basically, they react pretty much instantaneously. So you can see in some of these graphs, as soon as we hit that reference line and it peaks, that's when we get a change in the output. So it's not frequency regulated. It's basically just responding instantaneously to things. Yeah. And so comparators also only use positive feedback. So that's something important to note, where all of the inputs, they are going to be positive. Even when we see it dropping, like it goes above reference, it drops. it's still staying positive the whole time. And this just allows us to have very predictable DC output. And so we're taking an AC input essentially here, just a jagged wave coming in, and we are outputting a very clean high-low signal. And that's why, only using that positive feedback gives us that benefit. So these are made for high-speed switching. As I mentioned before, a larger slew rate, so it's going to move from that low to high state really fast, and it'll have a smaller propagation delay. So as the feedback gets fed back in and it goes through that balancing process, that happens much faster, which allows for less jitter on its way, and it just reaches that, balanced high state much faster. So the function of this, as you can see here, there's a symbol for a transistor. So it uses an internal transistor so that when the non-inverting terminal is greater than the inverting terminal, the output transistor turns on and it'll ground the output, basically complete that circuit and allow it to flow straight through to ground. Yeah, so that's one of the huge benefits of it is, it just flips it so that it can complete that circuit, and when it's not greater, it's going to close that circuit. Basically open, and it won't be able to flow through it, and so kind of only functions when something goes above that reference, and you can basically change how it reacts when something goes above that reference. Okay, so the component that I chose to talk about was the voltage level indicator. So as we see here on the right side, this is a very interesting circuit. Essentially it replicates like a battery charging level, where you've got different LEDs representing different charge levels. And so we've got 4 comparators connected here. So each of the inverting inputs is connected to our voltage input. And then we have on the non-inverting, those are all connected through a series of voltage dividers with the voltage source, and those are connected to ground. And so with having a bunch of voltage dividers, as it goes down, it'd be divided more and more and more. And so this least one would have the least amount of voltage being supplied to positive. So it would take the least amount of voltage applied to it on the input to basically turn it on and complete that circuit. And so that's why this would be kind of the low or first stage, second stage, third stage, fourth stage, or full battery, something like that. So when voltage is applied to the input, it is compared against the divided voltage from the source, and that's what completes the circuit if it's greater. So with no input, the non-inverting terminal is greater, and so this is going to open the comparator, so essentially nothing flows through it, and basically it will not allow it to connect itself to ground, which won't complete the circuit. And so when there's no voltage, nothing's going to flow through it. When voltage is applied to it and it overcomes that, so say in the slower one, it's overcoming that resistance, it's overcoming that non-inverting side. Basically what's going to happen is this is going to connect to ground. So it'll ground itself, and that's where we see voltage will now flow from the source over here, and it'll go through this resistor, through the diode, and through the comparator to ground. And so that's how, using that transistor and the combination of the 2 terminals, it will allow it to flow on this side, because obviously these are biased this way, from right to left. So it'll allow it to flow through that comparator to ground. And complete the circuit. And so that's how, this with the least amount of voltage being applied, because it's being divided the most, this one will turn on first, and then this one, and then this one, and then eventually that one. And so the potentiometer at the top here, this just allows for regulation over the entire circuit. So obviously this being the dominant resistor in the voltage divider, it's going to have the greatest effect over the entire system here, and basically determine how much voltage is needed between these inputs to cause things to turn on. And that's the end of the slideshow. So everything here that I referenced and all the photos, those were used from the Operational Amplifier book, or the Operational Amplifier chapter in the Practical Electronics book that we were supposed to read for this assignment. And I hope you enjoyed listening to this. Thank you.